There are moments in cosmic history so ancient, so violent, and so fleeting that they exist only as mathematical whispers, echoes etched into the structure of space-time itself. The first fractions of a second after the Big Bang form one such era, a moment so compressed and chaotic that the laws of physics as we know them dissolve into a primordial haze. In this ancient instant, long before stars, before galaxies, even before atoms, the universe may have forged some of its strangest and most elusive children, primordial black holes. Not formed by collapsing stars, but by the density fluctuations of a newborn cosmos. These black holes could be as small as mountains or as massive as stars, scattered invisibly throughout the universe like cosmic relics left behind by creation itself. As the universe expanded, these early fluctuations created pockets of extreme density, regions where matter collapsed inward faster than it could disperse. In these fleeting pockets, gravity achieved dominance for the first time, crushing the chaos into singularities. Unlike the black holes we know today, which are born in the deaths of massive stars, primordial black holes were born in the universe's first breath. They were ancient even before galaxies formed, older than light emitted by the first stars, older than the heavy elements that make planets and life possible. If they exist, they are relics from a time when the universe was not yet a place, but a process. And what makes them even more mesmerizing is the possibility that they never vanished, that they still remain, drifting silently across the cosmos, undetected but omnipresent. If true, they may be the missing mass of the universe, the mysterious substance we call dark matter, a form of matter that does not shine, does not glow, does not reflect, but whose gravity holds galaxies together, shapes cosmic structure, and silently governs the evolution of the entire visible universe. Primordial black holes are not just a scientific curiosity. They may be the shadowy foundation of everything we see. To understand why primordial black holes captured the imagination of physicists, we must first confront the enigma that is dark matter. Observations of galaxies reveal that their outer stars move far too quickly, so quickly that they should be flung into intergalactic space. And yet they remain bound, held tightly in a gravitational grip far stronger than the visible matter around them should allow. The same mystery appears in galaxy clusters, in gravitational lensing distortions, in the very pattern of cosmic microwave background radiation. Something massive and invisible pervades the universe, outweighing ordinary matter by a factor of 5. Dark matter is everywhere, yet we cannot touch it, see it, or interact with it directly. Conventional explanations suggest exotic particles that pass through matter effortlessly, but decades of experiments have not revealed a single such particle. And as the silence grew louder, physicists began revisiting an older idea, one nearly forgotten. What if dark matter is not a particle at all? What if it is made instead of countless tiny black holes, relics of the primordial universe? The idea is compelling because primordial black holes would naturally be invisible in every way dark matter is invisible. They would not emit light. They would not reflect or absorb it. They would be detected only by their gravity, the same way dark matter reveals itself today. And because they could range dramatically in size, from asteroid mass to mountain mass to stellar mass, they could populate the cosmos in vast swarms without ever forming luminous structures. A galaxy filled with such black holes would look exactly like a galaxy dominated by dark matter. Yet proving their existence is another matter entirely. A primordial black hole the size of a mountain could pass through the solar system and go unnoticed. 1 billion of them could drift through the Milky Way without ever revealing themselves. Only through subtle gravitational effects, microlensing events, cosmic background distortions, or their potential collisions could we ever hope to detect them. The universe hides its oldest children well. The search for primordial black holes has become one of the most ambitious quests in modern cosmology. Scientists scour the universe for the faintest clues, tiny flashes of light where none should be, brief distortions in the fabric of space-time, gravitational wave signatures that whisper of black hole mergers too small or too strange to have come from collapsing stars. Each clue is a fragment of a puzzle spanning 13.8 billion years. The first hints came from microlensing experiments, projects like MACHO, EROS, and OGLE, which watched millions of stars for signs of slight brightening as compact objects passed in front of them. These events provided tantalizing evidence. Some dark objects existed, but not in the abundance needed to account for all dark matter. Still, the data did not close the door. It narrowed the possibilities, forced theories to adapt, but left the core idea intact. If primordial black holes exist, they might simply be smaller or larger than these early surveys were tuned to detect. Then came LIGO and Virgo, detecting gravitational waves from black hole mergers. Some of these black holes were unusually massive, too massive for the end of typical stars. Their origins remain uncertain, and while they do not confirm primordial black holes, they do raise questions. Could some of the mergers LIGO detects be the unions of ancient singularities born before the first stars? Could we be listening to the collisions of objects older than time itself? The search continues across every wavelength of light, every ripple of space-time. Some scientists examine cosmic microwave background distortions. Others search for Hawking radiation from evaporating micro-black holes. Others model the evolution of the early universe, looking for conditions that might have produced the density fluctuations needed. Each approach offers a different path into the same fundamental mystery. And through it all, one possibility remains tantalizingly alive: that dark matter could be not an invisible particle, but an entire population of miniature black holes scattered like cosmic dust across the universe. In the grand tapestry of the cosmos, dark matter is the unseen thread that stitches galaxies together. It shapes the cosmic web, guides the formation of galaxy clusters, and sculpts the structure of the universe on scales far beyond our comprehension. Yet for all its influence, we know almost nothing about what it truly is. This is the paradox at the heart of modern cosmology. The universe is dominated by a substance that defies detection, eludes interaction, and resists every attempt to classify it. Primordial black holes offer one of the most profound possibilities ever proposed. They would be relics of a universe before physics stabilized, before atoms existed, before light could even travel freely. They would carry the memory of creation, not metaphorically, but literally, encoded in their very mass. They would be the fossils of a cosmic epoch beyond all direct observation. Whether primordial black holes constitute dark matter remains an open question. The evidence is suggestive but incomplete. The theories are compelling but unfinished. And the universe, as always, remains silent. But the pursuit of this mystery has reshaped how we think about both dark matter and black holes. It forces us to imagine a cosmos where ancient singularities drift unseen through our galaxy, their gravity shaping the motions of stars and planets, even as they remain forever hidden. In a universe defined by invisible forces and ancient phenomena, Primordial black holes remind us that the cosmos is not merely vast, it is deep. Deep in time, deep in structure, deep in mystery. They suggest that the answers to our greatest questions may lie not in the future, but in the earliest fractions of a second after the Big Bang.